Okay, everyone. So this topic is going to be similar to what we did for population proportions, determining the sample size. It's not that different. Now, so before we carry out a study on a variable, we would want to decide how large to make the sample size n. And generally speaking, a larger n will give us a tighter confidence interval, which is good, but it will require more larger sample requires more time, more money, more effort. So we want to make it as accurate as we can, but we don't want to make it too any larger than we need to. We don't want to make the sample size any larger than we need to. So now if we somehow knew the standard deviation x, sigma x, this is a big if, then the margin of error for our confidence interval would be this. And this actually goes back to um, the first video for this topic, where we said, well, this is an unrealistic situation. Usually we don't know sigma. So compare that with what we've been doing in the last two videos was we've been saying the margin of error was T alpha over 2 times S over square root of n. Now, um, we could try to use this formula, but we don't know S either, right? If we haven't done the study yet, we don't know S either, so this doesn't really help. Also, and here's a trickier point, the T depends on N, but that's exactly the thing we don't know, but we don't know N. So this formula has two problems with it, whereas this one only has one problem with it. So maybe this first one is better. Now, so if we take this, if we solve for n, what happens? So let's say I'm going to divide both sides by z alpha over 2, critical z value. What do I get? Sigma x over square root of n. And if I, let's see, if I cross multiply, you could say, I get square root of n is z alpha over 2 over e times sigma x. And that tells me that n is, I just need to square everything, right? Square both sides. So it's that squared over e squared, sigma x squared. So that's my formula for the sample size if somehow I know sigma x. And then we have to round up, right? Rounding up is the safe way to round. If we round down, we might be making the sample too small. So this will work, but we need some strategies. What if we don't know sigma x? What do we do? So if we don't already know sigma x, we can choose to do one of the following. We can use S in place of sigma if we have some sample data already. If we have sample data already from, let's say, like what you would call a pilot study. A pilot study is like a small initial study just to learn the basics from a pilot study. Or what else? You might have a theoretical basis for some estimate. So for example, i.e. like if we were talking about IQ scores, it's designed to have a sigma of 15. Now, it might not be 15 in a specific population, but it's designed to be 15, so that would be a reasonable estimate. There's a certain amount of what's the word here? There's a certain amount of judgment that's required. Is this a reasonable estimate of sigma, or am I kidding myself? And so it's better to err on the side of let's be more cautious. We'll use a larger sample than what this formula tells us. Um, Otherwise, later we might regret it. We'll get a confidence interval, but it'll be too wide, and then we don't get enough accuracy. So we'll use a larger sample size than we need. We'll err on the side of making it larger. Is there anything else? Any other? Well, basically the last thing would be using a sigma x from a previous study, which is similar to the first one, but maybe it's, say, a study from a few decades ago. You know, you're not sure if the population has changed, but we can use the same parameter sigma. Okay, so we're going to do a problem like this, one more, and we're going to analyze the mean body temperature data set, which is one of the data sets given on the Blackboard. But we don't need to pull up that data set because we're told enough here to do the question. So it's body temperatures, and it includes 106 different measurements. So let's start by writing down the sample size is 106. 106 body temperatures of adults for day 2 at 12 a.m. Okay, so if I remember correctly, each person had their temperature measured at a few different times. So this is the second day at midnight. And the minimum here, the minimum measurement was 96.5 degrees Fahrenheit, and the maximum in that data set was 99.6. Find the minimum sample size, this is what we're asked, find the minimum sample size required to estimate the mean body temperature of all adults. Assume that we want 98% confidence, so 1 minus alpha should be 0.98, which means alpha is 0.02. And we want the margin of error, the sample mean is within 0.1 Fahrenheit. So the margin of error is 0.1 degrees F. Okay, so let's think about this. What's our formula for n? It's going to be let's see, it's z alpha over 2 squared sigma x squared over e squared. And then we're going to, that was back here. And we're going to have to round that up. But let's think for a second, what do we already know? So we know the e. I can figure out the critical z value, but the sigma I don't know. Let's just put in the things we do know. So what is z alpha over 2? It's z of, what is alpha over 2? So alpha over 2 would be 0.01 here. 0.01. And how do I find a critical z value? 0.01. This is a standard normal. For z, it's a standard normal, so I use norm.s.inverse 0.01. What do I get? We're just doing the things we know first. Equals norm.s.inverse 1 minus 0.01. Almost got that wrong. 2.32635. This should be 1 minus, right? 2. What was it? 2.32635. Okay, now what about sigma? So now there's part A here is basically giving us some instructions for estimating sigma. Estimate sigma x. Now, I haven't mentioned this up to this point because it's not particularly important, but one way to find the sigma is to use what's called the range rule of thumb. Now, the range rule of thumb says that, now think of it like this. We know that for normally distributed data, most 95% of the data are within 2 standard deviations. So it's not that far off to say that all of the data is within 2 standard deviations. In other words, the whole range of the data is 4 sigmas, right? Because there's the middle, there's 2 to the left and 2 to the right. All of the data are within that 4 sigma range. So this rule says that take the range and divide it by 4. That's an estimate of sigma. And it's a pretty rough estimate, but it's a way to do it. So here the range is 99.6 minus 96.5. And we're saying if all of the data is within 4 sigmas, then that should be a rough estimate. 96.5 divided by 4, so I get 0.775 degrees F. So now I can do my calculation for n. N is z squared times sigma squared over E squared times so the margin of error, yeah. So I get 325.052 something something, so I rounded up to 326. So that's my answer for part A. Now it's saying, what if we do it again? Now estimate sigma using the S from the actual data set. It says, assuming that if we actually looked at the data set, we could calculate this ourselves, that S is 0.62. So if we approximate that sigma is 0.62, what do we get? So 0.62, now we get n is 2.32635 squared, 0.62 squared. It's going to be smaller. $208 point something. So rounded up 209. So that estimate allows us to derive a smaller sample size. Now, what's part C? It's probably going to ask us which one's better, right? Compare the results from A and B. Which result is likely to be better? Well, better, what does better mean here? Better means presumably it means getting a narrower confidence interval. In other words, i.e. getting within the margin of error that we desired. That we wanted. So likely the better one here is the first one. Better here would be the first estimate, which is 326. In other words, the larger estimate. Now, better, what does that mean? better could also mean which one will cost us less time and money. Then in that case, it would mean the smaller n will be better. But the problem with that is it might not give us the margin of error that we wanted. It might give us a larger margin of error in the end. And we would be disappointed because we'd have a result, but it would be kind of a vague result. We would say the body temperature mean is between this and this, but it's a very wide range. Okay, so we'll leave it there. And where we're going next is we're getting into hypothesis testing, which is it's based on almost the same ideas as confidence intervals. It's just organized in a slightly different way, and it's a kind of framework for making decisions, whereas confidence intervals require us to make an interpretation at the end. All right, I'll see you in that video.